99, proceeded, 3, 2, 1, ignition. Right away, Houston. Regs are good. Ag thought. Pitch over.
Roger, you have good thrust.
On December 14th, 1972, at approximately 5:54 p.m. Eastern Standard Time, the Apollo 17 Lunar Module Challenger blasted off from the surface of the Moon. At this exact moment, the final human beings to walk on the Moon to date officially left, and our nearest cosmic neighbor has been completely uninhabited since that time, at least by living things. Well, maybe. Put a pin in that living things comment, we'll come back to that. Despite the Apollo program being officially over, and crewed exploration coming to an indefinite close, we never exactly stopped exploring the Moon. The priorities of NASA moved on, both to crewed orbital infrastructure and robotic exploration of other planets. Not only were they not the sole people exploring, but they also went back a few times after that last pair of boots left, especially within the last 5 years. Today, we're going to do a deep dive into every spacecraft to explore the Moon following the Apollo program. But first, we need to talk about one experiment that lived for 5 years after the end of Apollo. Apollo 12 brought something called the ALSEP to the Moon, the Apollo Lunar Surface Experiments package. Primarily sensor experiments that measure solar wind, ions, and charged particles. One of these experiments was called the Passive Seismic Experiment, and is exactly what it sounds like. It measured the seismology of the Moon as it happened. While it was capable of measuring quakes within the Moon from time to time, its more immediate purpose was to measure impacts from external sources. More specifically, impacts of the S-4B upper stage of the Saturn V rocket and the ascent stage of the lunar module. Once each Apollo mission after Apollo 12 had been sent toward the Moon, the S-4B would be left on a trajectory that would crash it into the Moon's surface at a velocity of around 2.5 kilometers a second. Similarly, after astronauts returned to the command module, the ascent stage of the lunar module would also be sent on a crash course, both of these impacts being measured by the PSE. These were primarily used to calibrate the instruments, since the weight, speed, and impact location of these objects was known to the engineers. At the same time though, the impacts were a little surprising due to how far and for how long the shockwaves resonated through and across the lunar surface, with the smallest reverberations still being detected hours after the impact. For the 5 years after Apollo was over, the PSE measured disturbances throughout the lunar day, but noticed they were most focused during sunrise and sunset. While this might seem like it says something about the lunar day and night cycle, it was eventually concluded that most likely it was related to expansion and contraction of the mylar shroud around the seismometer, or the cable that connected it to the rest of the ALSEP. Though there were a few minor incidents, the PSE continued to function, creating detailed accounts of lunar seismic and tectonic information until September 30th, 1977, when the ALSEP was commanded to finally be shut down. At this point, Editing Deakus is going to make a quick appearance here. I kind of forgot to mention that Apollo 12 wasn't the only mission with a seismic experiment. In fact, all of them had one, including Apollo 11, though that first one ended up failing after 14 days. It was intended to be self-supporting, carrying its own power and communications, and was part of a more simplistic version of the ALSEP intended to be set up very quickly in the case of a possible mission aboard. The rest of the experiments don't have much info to add, and all 5 of the PSEs were shut down at the same time in 1977, as previously mentioned. Now, as we go through post-Apollo missions, I'm going to point out that I've done my usual thing here. I'm only including missions intended to explore and understand the Moon itself. A lot of spacecraft have performed lunar flybys because it's a very efficient way to reach other planets by performing a gravity assist maneuver out of the Earth-Moon system. However, unless they actually did scientific work with the Moon as a subject, we'll be skipping them. I suppose it shouldn't be too surprising that the first nation to visit the Moon following the end of the Apollo program was the Soviet Union. While the USSR's lunar program had a shaky start, it made some decent strides once they stopped focusing on crewed vehicles, including sample returns, the first lunar rover being Lunokhod 1, and more. This all occurred during the Apollo program and after it. The first post-Apollo mission was Luna 21, launched just under a month after Apollo 17. While the previous mission focused primarily on lunar soil sample return, Luna 21 was rover-focused, delivering Lunokhod 2, the second rover of the Lunokhod program. The first had beaten Apollo 15 to the achievement of first lunar rover by about 6 months, though of course Lunokhod rovers were robotic, not operated by astronauts on the surface. Lunokhod 2's primary objectives were to photograph the lunar surface with an improved TV camera from its predecessor, investigate the possibility of performing astronomy from the moon, perform laser ranging experiments with the Earth, and take a handful of local measurements of things like cosmic rays and magnetic fields. Part of its overall design included a round, hinged lid that covered the instrument bay. When it was open during the day, a solar panel on the inside of the lid would charge the batteries, and then when it closed to endure the long lunar night, a radioisotope heater unit would keep the instruments warm. Launched on January 8, 1973 aboard a Proton heavy lift rocket, Luna 21 arrived in orbit on the 12th, did 40 orbits around the moon with various adjustment maneuvers, and then its braking rocket was finally fired on January 15th, putting it into freefall. During descent, it used two sets of thrusters. Higher-powered main thrusters slowed its descent until about 22 meters above the surface, then smaller secondary thrusters finished the job. At 1.5 meters from the surface, all engines cut off, and the lander slowly fell and touched down in Le Monnier crater, which is located here. 3 hours were spent ensuring the lander and rover were in good shape, then finally, Lunokhod 2 disembarked and rolled down a small ramp onto the lunar surface. With an improved traction and camera system, the rover managed to outperform its predecessor on the first day, traveling over 6.5 miles. However, on the 9th of May, after a total distance traveled of around 26 miles, that's just under 42 kilometers by the way, Lunokhod 2 unintentionally came too close to a crater wall. The rover's lid brushed against the wall and spilled a fine-grained regolith onto it, and when the lid closed, that regolith was dumped onto the radiators. When the lid was opened later, the rover overheated and failed, and by June 3rd, a Soviet news agency announced that the mission was over. The rover, of course, remains there to this day, with its tracks having been imaged by the Lunar Reconnaissance Orbiter, which we'll be covering later, and has provided virtually all in-orbit views of older spacecraft as they sit on the lunar surface. After Mariner 10 scanned the lunar North Pole to test its instruments before heading to Venus and then Mercury, the Soviet Luna program continued with Luna 22, an orbital mission. The second of a new series of more advanced orbiters, Luna 22 successfully entered lunar orbit on June 2, 1974. Its mission involves study of gravitational fields, magnetic fields, mapping the surface, recording meteoroid activity, and similar things. What did it find out about these subjects? Yep. Thanks, Soviet Union. Editing Deakus here. I tried to do a little further digging, and yeah, there really isn't much of anything. The only experiment results I found are a dataset on particle count rates prepared at Moscow State University with NASA data restoration funding and published in ASCII format, and this GIF file of a graph that I don't think is particularly legible, and all of this was published in 1999. And people wonder why I'm not exactly a fan of the USSR. By the way, that's how you say my name, or at least how I say it. You can say it however you want, but I say Deakus, but nobody tell Fujikura Uruka.
Deakus? You're welcome, Deakus. No problem, Deakus. Thank you, Deakus.
Luna 23 came next, an intended sample return mission, which would have been the third mission to do so, except it tipped over. It was the first modified lunar sample return spacecraft, intended to return a deep core sample of the moon's surface, unlike the first two, which merely scooped up soil and rocks from the top layer. It was equipped with a new drilling and sampling instrument intended to dig 2.3 meters deep, but it never got the chance. During its descent about 130 meters from the surface, all altitude measurements from the Doppler radar stopped. Despite this failure, the lander did manage to touch down in one piece, at twice the intended landing speed, 11 meters a second instead of 5. The hard landing damaged equipment, depressurized the instrument compartment, and caused a transmitter to fail. Attempts to activate the drill failed, and the primary mission was abandoned. A makeshift secondary plan to collect limited data was conducted until 12 days into the mission, at which point all contact was lost. In a beautiful foreshadowing of a number of 21st century landings, the Lunar Reconnaissance Orbiter in 2012 revealed that Luna 23 was laying on its side, finally answering precisely why it was unable to do any drilling. If you've seen previous videos of mine on exploration of other planets, and if you haven't, please go watch them, I worked really hard on them, you'll know that during these days, the Soviet Proton rocket was not particularly reliable. What would have been the next Luna mission, another sample return, would later be named Luna E-8-5M number 412 and never made it to orbit. This was a common Soviet tactic. Only successful missions got named in the correct order. Failures would be given a special designation, usually Cosmos followed by a number. In this particular case, the upper stage of the rocket suffered a failure of the LOX turbopump, that's as specific as the report gets, and the probe failed to reach orbit, crashing back to Earth on October 16, 1975. Luna 24 would be launched in August of the next year, virtually identical to the previous failed probe. A small ascent stage with a spherical re-entry capsule derived from the instrument compartment of the Lunokhod rover, which sat on top of a descent stage that was also the same as those used for the rover. This time around, the mission was entirely successful, landing only a few hundred meters away from the toppled Luna 23. It drilled about 2 meters into the soil as intended, stowed the sample away, and lifted off on August 19th. Its ascent engine, capable of firing only once for 53 seconds, sent it on a free return trajectory to Earth, where it landed safely in western Siberia, and the returned soil was analyzed. In December, the USSR swapped a gram of their sample with that of an Apollo sample from NASA for comparison. Then in 1978, 2 Soviet scientists published a paper stating that there was definitive detection of water in the soil sample, about 0.1% by mass. However, not only was this report never confirmed by other researchers, it was also noted that the paper was not willing to completely rule out terrestrial contamination. No definite proof of water on the moon, yet. Luna 24 was the final lunar spacecraft launched by the Soviets, and will be the last to make a soft landing until 37 years later. The next several missions were orbital in nature, though the first would at least touch the surface. Hi-10, a Japanese spacecraft built by the Institute of Space and Astronautical Science, was launched in January of 1990, some 14 years after Luna 24. ISAS, by the way, was effectively a predecessor to JAXA, the modern Japanese space agency, established in 1964 and playing a major role in Japan's development of spaceflight technology. Japan took something of an odd path to spaceflight growth, in no small part due to the banning of aircraft development after World War II under the Allied occupation of Japan. Many aeronautical engineers were made jobless until the San Francisco Peace Treaty, when a new aviation research group at Tokyo University began to work on developing rocket technology. I'm saying all of this because this little teaser may justify a full video on Japanese spaceflight history if there's an interest for it. Hi-10 was a cylindrical probe intended to be placed into a very high elliptical orbit of the Earth, causing it to repeatedly swing past the Moon at the height of its journey around the Earth. The original injection burn left it with a lack of velocity, which was then corrected with the attitude control thrusters, allowing it to make the first low-energy transfer toward lunar orbit. This capture into a temporary lunar orbit cost the craft exactly 0 delta V, but also took 5 months instead of the 3 days required for a normal Hohmann transfer. The probe had only one scientific instrument, serving more as a proof of concept for Japanese lunar probes, the Munich dust counter, used to look for trapped dust particles at the L4 and L5 Lagrange points. It didn't really find anything significant with this, and was then placed into a permanent lunar orbit in February of 1993. It remained there until April, when it was deliberately crashed into the lunar surface on April 10th, officially making Japan the 3rd country to impact the surface of the Moon. Clementine, in 1994, was a NASA spacecraft intended to perform ultraviolet, infrared, laser-ranging altimetry, gravimetry, and charged particle measurements of both the Moon and a near-Earth asteroid. It was a simple octagon bus with 2 solar panels and a high-gain antenna at one end, with a thruster at the other end. It achieved attitude control with a combination of a hydrazine system of 12 jets, 2 star trackers, and reaction wheels. Launched on a Titan II in January, Clementine spent 2 Earth flybys getting ready, then entered orbit of the Moon a month after launch. It spent 2 months mapping the surface in 2 phases. For the first, it entered an elliptical polar orbit, then rotated that orbit slightly after a month. It obtained global imaging and altimetry coverage from 60 degrees north to 60 degrees south, taking 300 orbits to do so. Following this mapping mission, the spacecraft was supposed to head to 1620 Geographos, a highly elongated near-Earth asteroid approximately 2.5 kilometers wide. Clementine was brought back into an Earth transfer orbit, flying by the Earth twice and preparing to be launched toward the asteroid with a gravity assist. At this point, the craft suddenly began to spin. Over a period of 11 minutes, its fuel supply was used up entirely by a stuck attitude control thruster, the firing of which sent it into an 80 RPM roll. Its asteroid flyby immediately became useless, so it was instead put into a geocentric orbit to test components as it repeatedly flew through the Van Allen belts. Its mission was officially concluded in June of 1994, but 4 years later, NASA announced that data obtained indicated the presence of water in the Moon's polar craters, enough to support a human colony and a rocket refueling station. It was these kinds of results, coupled with the earlier hints from the later Luna program, that would eventually renew interest in a return to the Moon. Back in 1990, then Administrator of NASA Daniel Goldin proposed the policy of faster, better, cheaper planetary science missions. Prior to this, Missions were so expensive and heavily delayed that failures weighed heavily on the agency, so this policy was intended to allow for more risks with lower consequences, yielding overall higher amounts of success at the same time. While a good policy, I'm not sure how well the agency eventually stuck to it, considering Golden's recommendations also heavily influenced the James Webb Space Telescope, which was incredibly expensive, incredibly slow to develop, and had hundreds of potential failure points that would have cost billions had they occurred. Nevertheless, part of this faster, better, cheaper policy was the Lunar Prospector, part of the Discovery Program. Founded in 1990, the Discovery Program was intended to begin implementation of Golden's policy. Missions are solicited through a call for proposals on science topics, and selected proposals are then led by a scientist who helps build the mission around that science topic. They also allow for partial funding by offering other agencies and universities to contribute individual experiments that can be added to the mission, and other cost-saving measures that might include repurposing existing spacecraft for new missions. Lunar Prospector was the third mission in the program, following Near Shoemaker and Mars Pathfinder, intended to map lunar surface composition, as well as measure magnetic and gravity fields from a low polar orbit. Lunar Prospector was composed of a 4-foot 2-inch tall graphite epoxy drum, with 3 instrument booms that extended out from it, and body-mounted solar cells lining the outside of the drum. The booms carried 6 instruments, from a gamma-ray spectrometer to electron reflectometer and magnetometer. Launching on January 7, 1998 aboard an Athena 2 rocket, one of 3 launches that rocket ever made, it was sent on a 105-hour cruise to the moon and deployed its instruments, after which it successfully entered lunar orbit. Its mission was entirely successful, mapping the surface of the moon until July 31, 1999. At this point, it was crashed into a permanently shadowed area of the Shoemaker crater near the South Pole, hoping to send up a cloud of ice deposits that could be observed from Earth. Unfortunately, no cloud was seen. Results from the mission were varied. Important elements found on the moon were uranium, thorium, and potassium. Further evidence for lunar water ice was gathered by the neutron spectrometer, and the first gravity data was obtained. However, the data was only on the near side, as the experiment required line-of-sight tracking with the Earth, making it ineffective on the moon's far side. Prospector would be the final lunar mission of the 20th century, with the next coming in 2003 with a new contender entering the ring, ESA. SMART 1, standing for Small Missions for Advanced Research and Technology 1, was launched on September 27th from French Guiana aboard an Ariane 5 rocket. It's the first spacecraft to explore the moon that utilized a Hall effect thruster, which gives me a chance to do some extra explaining. Traditional chemical combustion engines work by burning a fuel and an oxidizer in a combustion chamber, the reaction releasing energy in the form of hot expanding gases, which are then forced out of the nozzle at high speeds to produce thrust via Newton's third law. An ion thruster, however, accelerates charged particles using electric or magnetic fields. The propellant, usually xenon gas, which was the case with SMART 1, is ionized and accelerated through a magnetic field, again creating thrust with Newton's third law. Ion thrusters are much more efficient, requiring a lot less propellant, but the mass flow rate is much smaller. Essentially, it's a gentle and slow push to high speeds, rather than an explosive fast one. They're exceptionally effective for deep space maneuvers, though at this point in their development, they could never get a launch vehicle off of the ground itself. Because of this, SMART 1 made orbital maneuvers in segments rather than one short burst, waiting until the low point of the orbit to fire the thruster and gradually extend the high point to where it needed to be. Rather than a set goal of making specific lunar discoveries, SMART 1 was more of a technology demonstration, very commonplace when an agency makes a first-of-its-kind mission. It featured a suite of instruments that were entirely new and untested, and the spacecraft was used to confirm that they all worked. A micro-imager experiment was used to provide high-resolution images of the lunar surface and test a new method of compressing the images for a high-performance transfer rate back to the Earth. A compact X-ray spectrometer was also tested, as well as an X-ray solar monitor to watch the sun's solar variability, a diagnostic package to assess the ion thruster, and an electron and dust experiment that measured both the emissions of the thruster, as well as the wake left by the moon's movement to solar winds. SMART 1 spent over a year extending its Earth orbit out towards the moon, entering lunar orbit in November of 2004. It then spent 2 years using its instruments until it impacted the surface on September 3, 2006. The planned crash was supposedly visible with ground telescopes, though I couldn't find images of this, so I can't actually confirm that, and like with Prospector, the hope is that water ice and other subsurface materials would be exposed by the impact for later analysis. Editing Dekus here again. Boy, I really dropped the ball. Here is an animation of the flash generated with images from the Canada-France-Hawaii telescope, here's one built from infrared images from the same telescope, and here is a still image of the flash occurring. This is like the sloppiest video I've ever made. I'm sorry, I'll do better in the future. The next lunar mission was Artemis. No, not that Artemis, we'll get to that. I'm talking about the Themis mission, or Time History of Events and Macroscale Interactions During Substorms. Very catchy. This was a constellation of 5 satellites intended to study Earth's magnetosphere, and 2 of them, Themis B and Themis C, were moved into lunar orbit and renamed Artemis P1 and Artemis P2. In this case, Artemis stands for, wait for it, Acceleration, Reconnection, Turbulence, and Electrodynamics of the Moon's Interaction with the Sun. However, these probes are more focused on the Earth and are simply using the Moon as a remote viewing location for the mission. So we're going to move on from these, but I at least wanted to mention them and give you enough information to learn more about them if you so choose. In 2007, Japan returned to the Moon with Selene, better known in its homeland as Kaguya, named after a lunar princess in a Japanese folktale. Produced by the ISAS and operated by JAXA, Kaguya was launched on September 14th aboard a Mitsubishi H-2A rocket. It actually consisted of 3 spacecraft: the main orbiter and 2 small tertiary satellites named Okina and Ouna. Ouna used what's called very long baseline interferometry to map the Moon's gravity field, useful when it's close to the lunar limb where Doppler measurements stop working. Basically, VLBI is a way to map images by combining the collected data picked up by multiple ground-based receivers, sort of like using 2 eyes to give you better depth perception than 1. Okina, on the other hand, was a small relay satellite, intended to keep radio contact with the orbiter when it was on the far side of the Moon. This allowed Doppler shift measurements to continue to work on the lunar far side, creating the first full accurate gravity field measurements of that side. The main orbiter carried a host of 13 scientific instruments with the expressed goal of obtaining, quote, scientific data of the lunar origin and evolution to develop the technology for the future lunar exploration. Kaguya completed its main mission in October of 2008, but kept going until June of 2009, when a degraded reaction wheel led to it being intentionally crashed into the surface. Not only did it provide the first gravity map of the Moon's far side, but it also gave the first optical observations of the permanently shadowed Shackleton crater at the lunar South Pole, evidence of Earth's oxygen being transported to the Moon via the magnetosphere, and some of the most detailed lunar topography maps to date. Just look at this footage. Absolutely beautiful. The data was provided to Google for free, resulting in the Google Moon that we can all see and use today. Selene helped renew global interest in exploring the Moon, with some calling it the, quote, largest lunar mission since the Apollo program, and spurring on future missions and plans to finally put boots back on the surface of our nearest cosmic neighbor. Back in 2004, the China National Space Administration, or CNSA, started the Chinese Lunar Exploration Program, a 4-phase program that plans to end with the development of a robotic research station near the South Pole, as well as crewed landings and a possible outpost. The first phase entered operation in 2007 with the launch of Chang'e-1, a simple box-shaped orbiter with the stated goals of obtaining 3D images of the lunar surface and analyzing surface chemical composition. A large portion of Chang'e-1 was proof of concept. Being China's first attempt at exploration beyond low Earth orbit, large portions were dedicated to simply ensuring they knew how to do it. Now, bear in mind, the CNSA lacks the transparency of a lot of other space agencies. There's a large amount of information that we're simply not privy to, so apologies if sections of this video detailing Chinese spacecraft are a little lacking. Blame the CCP, I suppose. Anyway, Chang'e-1 launched in October of 2007, making 3 orbits around the Earth while gradually extending the apogee until a final translunar injection burn at the end of the month. Lunar orbit was achieved on November 5th, and to celebrate, the probe transmitted back a series of classical Chinese musical pieces. It remained in lunar orbit until March of 2009, when it was crashed into the surface and its mission ended. What did it achieve? Well, it created an accurate high-resolution 3D map of the lunar surface, for one. Want to see it? Not too bad. I've got this image of topography from laser altimeter data via Wuhan University, and this small section of 2 volcanoes on the lunar near side, but I've been unable to find a full 3D map. We're entering a veritable battery of new contenders at this point. In October of 2008, India entered the ring with the first probe of the Chandrayaan program, appropriately named Chandrayaan-1. What does Chandrayaan mean? It means moon vehicle. Nice. I love a direct approach. It consisted of 2 parts, an orbiter and an impactor, the latter of which was again named near Shackleton crater, making India the 5th national space agency to reach the lunar surface. The orbiter, intending to operate for over 2 years, ended up lasting just over 10 months. In August of 2009, the orbiter's star tracker failed, and his thermal shielding seemed to be inefficient as it was overheating. On August 28th, the orbiter stopped communicating after 312 days, however, it achieved most of its intended objectives. One of the highest achievements was the finally confirmed discovery of widespread presence of water molecules in the lunar soil. It was also the first spacecraft to provide photographs of the Apollo lunar landing sites showing the shapes of the LEM descent stages still on the surface. Subsequent missions would continue to do this with increasing resolution, especially our next mission, the Lunar Reconnaissance Orbiter. The first spacecraft we've covered that's still operating today, the LRO, launched in June of 2009. It's responsible for the most detailed images of the moon to ever exist, in particular providing images of previous and current lander missions, from the Apollo sites to the toppled Luna 23 to future missions that we've yet to cover. With an array of 6 instruments at its disposal, this large spacecraft has provided the most accurate topographic map to date and provided more than 192 terabytes of data over the course of its continuously extended mission. Intended to operate only for a single year, it entered its 15th year of service in June of 2024. In the following July, analysis of its gathered radar data confirmed the presence of an underground cave on the moon accessible from the surface. It's believed to be about 40 meters wide and at least 80 meters long, existing in the massive lava plain of the Sea of Tranquility, which Apollo 11 landed on the edge of in 1969. The LRO has had a handful of amusing incidents over the course of its lifetime. First, I should probably mention that it was launched alongside another satellite, the Lunar Crater Observation and Sensing Satellite, or LCROSS. Intending to further explore the presence of ice water discovered by Chandrayaan-1, it succeeded in finding some in the southern lunar crater of Cabeus. Its Centaur upper stage was designed to crash into the crater, and when it did, LCROSS monitored the impact. The crash released the equivalent of 2 kilotons of TNT, and the resultant plume provided LCROSS with enough data to confirm the presence of lunar water. Interestingly enough, this impact was reported to be observable from Earth by the media, but this was not actually the case, mostly due to the crater being permanently shadowed. In 2021, the LRO was expected to come dangerously close to Chandrayaan-2, which we'll talk more about later, over the North Pole. However, to avoid a possible crash, Chandrayaan-2 performed a collision avoidance maneuver, keeping both spacecraft safe to this day. The second spacecraft in the Chinese lunar exploration program, Chang'e-2, launched in October of 2010. Similar in design to the first, it was actually modified from a backup of that first probe. It featured some improved instruments as well as a more precise mission. It flew 100 kilometers lower than the first, allowing for more detailed imagery and more precise science data, partly for plotting out a potential landing site for the next mission. In November of 2010, the Chinese government announced that its mission had succeeded, and 2 years later would release a complete lunar map from the constructed data, claiming it to be the highest resolution map of the entire moon yet recorded, though I'll leave the truth of that for you to decide, as the full dataset has been available for free download since April of 2018. After completing the lunar mission, Chang'e-2 left lunar orbit headed for the Earth-Sun L2 Lagrangian point to test Chinese tracking and communication abilities. It then left L2 to fly by the asteroid 4179 Totatis, which occurred in December of 2012. It obtained some very nice close-up images of the asteroid from a distance of just over 3 kilometers away. The spacecraft then headed into deep space, reaching over 200 million kilometers away from the Earth. In 2014, its weakening signal caused loss of contact, and the mission is officially well over, though the probe is estimated to return to Earth's vicinity sometime around 2027. It is at this point I'm going to take note of something. When I announced I was going to make this video next, a few people were skeptical that there would not be enough content for a good length video. I knew immediately this wasn't correct. There has been a lot of lunar exploration post-Apollo, especially in the 21st century. Bear in mind that we're in 2011 right now. Guess how many spacecraft are left? Go ahead, guess. There's 25. Here we go. The Gravity Recovery and Interior Laboratory, or Grail, was launched as part of NASA's Discovery program in 2011 aboard a Delta II. It consisted of an A and B spacecraft nicknamed Ebb and Flow, which were used in tandem to obtain data on the gravity field and geological structure of the moon. Able to detect very small changes in distance between one another, it would use this data to make inferences about the distribution of the moon's mass, which is much less uniform than one might expect. This is the reason low-orbiting lunar probes will eventually impact the surface. Though there's not enough atmosphere to pull them down due to friction, they will eventually instead have their orbits altered by these differing masses within the moon, eventually bringing them into a crash course. Grail used the information gathered to obtain data that would help determine the size of the moon's inner core and refine our understanding of its deep interior structure. Its mission took place over 88 days, performed after a low-energy transfer orbit of just over 3 months. At the end of a short mission extension, both spacecraft were crashed into a lunar mountain, almost right next to each other and moments apart, on December 17, 2012. The crash site had no name at the time, and after the fact, NASA announced that they would name it after Sally Ride, the first American woman in space and collaborator on the Grail project. Ride sadly passed away earlier that year in July. I spent about 20 minutes trying to come up with a pun to introduce the next spacecraft, and I just can't do it, Ladee. It's called Ladee. That's the joke.
Oh, brother, this guy stinks!
I'm so sorry. Anyway, Ladee stands for Lunar Atmosphere and Dust Environment Explorer. Designed specifically to study the lunar exosphere and dust surrounding the satellite, Ladee orbited the moon for just over 7 months after being launched by a Minotaur 5 on September 7, 2013. And I would be remiss if I just forgot about the fact that the launch of Ladee has maybe my favorite photo of a rocket launch ever. Do you see it? Zoom and enhance. Yeah, that frog is super dead. From 1956 onwards, scientists had theorized a tenuous atmosphere on the moon, very thin, consisting of constantly moving particles that rise up and fall back to the surface, a theory that seemed to be emboldened when Apollo crews saw glows and rays from the horizon during lunar twilight. Ladee was designed to try and confirm this theory. After 3 phasing orbits around the Earth, Ladee entered lunar orbit on October 6. Its first step was to perform a technology demonstration, setting a downlink record using its lunar laser communication demonstration and carrying out tests over the next 30 days. This was the first time two-way space communication was done using an optical laser instead of radio waves, and the extreme success of the results are likely to lead to more in the future. Ladee began a 100 Science Day phase in November of 2013. There was a brief period of concern during December when the Chang'e-3 lander was in operation. Concern that its engines would contaminate the tenuous atmosphere as landing disturbing the fine lunar dust and disrupting the mission occurred. However, it ended up providing additional data, since all of the values of the spacecraft's fuel was known. They knew how much fuel it would expel and what was in the fuel, so they were able to track the exhaust as it was distributed and eventually dissipated. Ladee was initially expected to go offline during the April 2014 lunar eclipse, as it wouldn't be able to generate power in Earth's shadow. However, it emerged from the 4-hour eclipse with only minor problems with a few sensors, though it was intentionally crashed into the far side of the moon on April 18th. Now, back to Chang'e-3. As mentioned, it was launched in December of 2013 and was the first lander of the Chinese program. The lander itself was mostly a technology demonstrator, serving as the deployment platform for the U-2 rover, as well as having a couple of cameras, a soil probe to test sample return techniques, and an ultraviolet telescope for deep space observations. The U-2 rover is the true highlight of this mission, having begun development all the way back in 2002. A 6-wheeled vehicle with likely inspiration from NASA's Mars exploration rovers Spirit and Opportunity, it carries an array of spectrometers on a robotic arm for surface analysis. Powered by twin solar arrays, it's able to operate throughout the lunar day and then enter a hibernation period during the night, with heaters keeping the instruments warm via radioisotopes. Chang'e-3 landed on the moon on December 14, 2013, marking the first soft touchdown since 1976 and making China the 3rd nation to land a spacecraft. 7 hours later, after checking the instruments, the rover was deployed. 3 days after the deployment, it was reported that the rover and all of its instruments were, quote, functioning as hoped despite the unexpectedly rigorous conditions of the lunar environment. The rover stayed stationary until December 20th, at which point it performed a 2-day mission of moving around the lander in a circle and photographing it from multiple angles. The 2 crafts then began their separate missions, and near the end of the second lunar day, bear in mind that's Lunar Day, so this was at the end of January 2014, the rover started having problems. It suffered some manner of short circuit, preventing it from properly entering a dormant state for the lunar night by folding its mast and solar panels. When the sun rose at the end of this second long night, Mission Control was unable to re-establish communication and it was declared inoperative. However, just 1 day later, on February 13th, they managed to obtain a downlink again, but the rover wasn't moving and it was experiencing significant problems with its instruments. By the 14th lunar day, the U-2 rover was more or less inoperable, though it did exceed its 3 months expected lifetime. It continued to transmit data until August 13, 2016, and the mission was officially ended. When did the lander's mission end? Well, it didn't. Surprisingly, Chang'e-3 remains operational 11 years after landing. The solar panels and radioisotope heater unit can potentially last for up to 30 years, so barring any electrical or communications failure, it's going to sit there and continue to transmit for a long time. Now, we're going to continue with China's lunar program, so you would assume that next is Chang'e 4, right? Yeah, you'd think that, wouldn't you? You fool.
You fool!
Chang'e 5T1 launched on October 23, 2014. An experimental robotic spacecraft used for atmospheric re-entry testing, the craft was effectively a technology demonstration for sample return. By this point, China was a decade into its crewed Shenzhou program, but that capsule returned from low Earth orbit. Returning from the moon with, say, a sample return probe is a much higher energy task which requires a much sturdier design, and 5T1 was intended to test this. Consisting of a Chang'e 2-like service module which carried a prototype Chang'e 5 return capsule, it was launched on a Long March 3C rocket into a lunar free return trajectory. Effectively, it would loop around the moon and return to Earth, hitting the atmosphere at the high speeds of around 11 kilometers a second rather than the usual LEO speeds of around 7 kilometers a second. The Long March 3C third stage was left in orbit between the Earth and the moon, impacting the latter 8 years later, in October of 2022. The CNSA denied that it was theirs, stating that it had already burned up in Earth's atmosphere and creating a brief media buzz as speculation arose that it could have actually been the Falcon 9 second stage that had launched the Discovery satellite. However, multiple observatories confirmed that it is almost certainly from Chang'e 5T1. The service module, however, was transitioned into lunar orbit and, as far as we know, is still there, last heard by radio astronomers in late 2020. Chang'e 5T1 carried a secondary payload, the first commercial payload ever sent to the moon, the Manfred Memorial Moon Mission, made by the German company OHB System and operated by Lux Space. It was a simple briefcase-sized probe with a mass of only 14 kilograms. Permanently attached to the Long March third stage, it held two simple instruments: an amateur radio experiment that was used for a contest with amateur radio operators around the world who tried to receive transmissions from the probe, and a dosimeter that measured ionizing radiation as the vehicle passed through the Van Allen belts. This secondary payload ceased operations in November of 2014 and impacted the moon along with the upper stage in 2022. So, how did the re-entry capsule do? Pretty good, at least as far as we know. Again, Chinese secrecy makes a reappearance here, but given their next steps in the program, the mission did seem to be a success when the return capsule landed in Inner Mongolia in October of 2014 after performing a high-speed skip re-entry. This method, utilizing multiple dips in and out of the upper atmosphere, both lowers heating loads and extends the ballistic trajectory further than a normal re-entry. Continuing the extensive battery from the CNSA lunar program at this time, the Keqiao Relay satellite was launched next in May of 2018. There isn't too much to say about this one. It's a relay satellite launched alongside a pair of microsatellites which would perform interferometry, though one never made it to lunar orbit. With only one operational, the interferometry mission couldn't be done, though the active satellite was equipped with a micro-optical camera, which allowed it to return color images of both the Earth and the lunar surface. It was eventually crashed into the surface in 2019, but the relay satellite continues to be active, serving as a communications point for further missions to the moon. In addition to this, it also carries the Low Frequency Explorer, a joint experiment with the Netherlands to detect early universe faint radio signals. Now we reach Chang'e 4, built out of a backup of Chang'e 3 with some adjustments for new objectives. Consisting of a lander and a rover, being U-2-2, it was launched on December 7, 2018, entered lunar orbit 5 days later, and landed on January 3, 2019, becoming the first spacecraft to touch down on the far side of the moon. The previously launched relay satellite allowed for communication with the craft without line of sight, being in a halo orbit that allows it to see the lander for the majority of its path around the moon. The landing site was a very large crater known as the Aitken Basin, thought to be an impact crater that exposed deep layers of the moon's interior, and the rover was intended to explore some of the unique geological features of that crater. U-2-2 was intended to extend the record of the previous rover, learning from its experience to make it operable for, quote, a few years, rather than the 3 months it was originally designed for. By 2019, it had become the longest-lasting lunar rover, breaking Lunokhod 1's record of 322 Earth days. The mission also marks the first major collaborations between the United States and China for space exploration, with scientists from both sides discussing possible observations with each other's spacecraft in lunar orbit and the coordinates of the lander after it touched down. In January of 2020, China released large amounts of data from the Chang'e 4 mission, including high-resolution images of the process of lunar ejecta formation created by impacts to the surface. The lander and rover both continue to operate to this day, with Yutu-2 being the only active rover currently on the moon. We're about to enter a battery of new landers that aren't going to go very well, and one might begin to wonder, how on earth did Apollo make 6 out of 6 successful landings in the 60s and 70s, yet modern landers rarely seem to get it right at all? The answer is surprisingly simple: people. The Apollo landers, being crewed, had a critical advantage that uncrewed landers don't. While the LEM did have its own automated guidance systems in regards to final approach and landing, they also have an essential backup: human intuition. A computer might not notice that it's about to land on a rock and tip over. It might not realize that its laser altimeter is only looking at a portion of the landing site. It might not realize that its own programming has become garbled and the numbers it's reading are no longer accurate. Human eyes can visibly see incoming hazards like craters and steep slopes, and throughout Apollo they often did, steering the LEM manually to a more safe location. So as a result of there being no humans involved, we're about to see a lot of failures on the road ahead. First up is the Beresheet lander, a demonstrator lunar lander developed by Space.il and Israel Aerospace Industries. A fairly small vehicle, it stood about 4'11" and wasn't very robust in terms of science value. It held a magnetometer and a laser retroreflector, but the only other payload was a time capsule that included a full copy of the English language Wikipedia, the Torah, children's drawings, and more. At the last minute, genetic samples and tardigrades were added, and there's a reason that's significant. Let's take the pin out of that living things comment I made at the beginning of this video. If you're unfamiliar, tardigrades are microanimals found all over the Earth and are pretty well known for their resilience to harsh conditions. Extreme cold, extreme heat, and even the open vacuum of space have proven ineffective at ending their lives. They're capable of suspending their metabolism and going into a kind of stasis-like state, remaining alive without food or water for several years at a time. In 2007, a Russian spaceflight mission exposed tardigrades to space for 10 days, and when they were brought home, 68% of them were able to be reanimated, and many even produced viable embryos. So just bear in mind that this lander held several of these guys. The Beresheet lander was launched in February of 2019 as a secondary payload to a telecom satellite aboard a SpaceX Falcon 9. It extended its Earth orbit 4 times to reach the moon and entered orbit on April 4th and attempted landing on April 11th. During descent, a gyroscope failed, causing the engine to shut off, and the ground crew couldn't reset the component due to a sudden loss of signal. Once communications were back online, the lander had gotten too low to slow its descent in time. At 150 meters in altitude, the last telemetry reading was received, which showed a velocity of over 500 kilometers an hour. When it hit the moon, it was completely destroyed. The real question is, did the tardigrades survive? We may never know, but for a brief period in time, it is possible that there was Earthborn life on the moon for the first time since 1972. ISRO, that's ISRO, the Indian Space Research Organization, continued their lunar program in the same year, launching Chandrayaan-2 in July. A rather ambitious mission, it consisted of an orbiter, the Vikram lander, and the attached Pragyan rover. The orbiter was entirely successful and continues to operate today, having been extended from a 1-year mission to now around 7.5, or so they're hoping. The Vikram lander, however, after detaching from the orbiter and descending toward the surface, deviated from its planned trajectory around 2 kilometers from the surface, and when touchdown was expected, contact was lost. ISRO Chairman K. Sivian would later state that, quote, "It must have been a hard landing, though no technical details of this failure have been made public at this time." However, despite the failure of the lander, the orbiter's mission has been wildly successful, detecting an abundance of sodium on the moon, more water molecules, and done significant study of the distribution of gases in the tenuous lunar atmosphere. The Chinese program continued in the next year, launching Chang'e 5 in November of 2020. This time, the mission was primarily focused on sample return, consisting of 4 parts: an orbiter, a lander, an ascender, and a returner. The 4 pieces launched together, with the lander and ascender separating once in lunar orbit. They descended to the surface, landing successfully on December 1st. Samples were collected via drills in the lander, which then transported them up into the ascender. On December 3rd, the ascender lifted off, returning to the orbiter and docking to it. It then transferred the samples to the returner aboard the orbiter and disconnected, deorbiting itself into the moon, while the orbiter returned to Earth. Shortly before re-entry, the returner was separated, performed a skip re-entry, and landed. This made China officially the third country to return samples from the moon, as well as the third country to discover a new lunar mineral, Chang'e Y, which appears as a colorless transparent crystal in basalt particles on the moon. Capstone launched next, a small CubeSat delivered to a unique lunar orbit by Rocket Lab's Electron rocket in June of 2022. Technically part of NASA's Artemis program, Capstone, standing for Cislunar Autonomous Positioning System Technology Operations and Navigation Experiment, good God, is effectively a test run for the Lunar Gateway space station. The intended orbit for the station is called a near-rectilinear halo orbit, which is moon-centric, but technically in orbit at the L2 Lagrangian point, which passes close to the moon at its perigee, described as balanced on the edge of the lunar gravity well. The use of NRHO for Gateway was first considered in 2018 due to its stability. It has low fuel requirements for station keeping and isn't nearly as affected by the moon's uneven mass. This would allow Gateway to serve as a kind of central hub for the Artemis program, a communications relay, a science lab, a short-term habitat, and a temporary holding area for uncrewed vehicles. However, there's been a lot of questions and criticisms regarding the effectiveness of Lunar Gateway. One former administrator, Michael Griffin, has stated the Gateway is only useful much later in the Artemis program, once it achieves fuel production on the lunar surface, at which point it could serve as a propellant depot. Others have made more general complaints that Gateway is a cost drain on the already expensive Artemis program, being largely unnecessary when already present elements can fulfill the same purpose. George Abbey, former director at Johnson, said, quote, "The Gateway is, in essence, building a space station to orbit a natural space station, the moon. If we are going to return to the moon, we should go directly there, not build a space station to orbit it." Regardless of the future of Gateway, Capstone launched successfully, and then promptly stopped responding after separating from the upper stage. However, a day later, contact was re-established, though the craft appeared to be tumbling. The problem was traced back to a thruster valve that was probably partially open, producing thrust every time their propulsion system was repressurized. By October of 2022, the team had uploaded recovery commands that stopped the tumbling and fully regained control, allowing Capstone to perform a lengthy ballistic transfer that sent it out to 1.5 million kilometers from the Earth, then back toward it where it intercepted the moon and entered NRHO in November. It remains active after an extension of its original 10-month mission plan, performing experiments and keeping careful track of its novel orbit. The newest country to explore the moon, South Korea, launched its first mission, Danuri, aboard a Falcon 9 in August of 2022. Largely a technology demonstration, it is currently in orbit surveying lunar resources and picking out future landing sites for the next phase of the Korea Aerospace Research Institute's lunar program. There unfortunately isn't too much to say about it just yet, though I will highlight the Shadow Cam, a hypersensitive optical camera that maps the reflective properties of permanently shadowed regions, helping to search for ice deposits. Here is its first photo of Shackleton Crater. The technology of Shadow Cam is heavily based on the narrow-angle camera of the LRO, but is much more sensitive, making it capable of capturing more details of these perpetually dark craters. Next comes the big dog. NASA's Artemis program, years in the making, decades if you count Constellation before it, finally saw its first true launch in November of 2022. I could probably make an entire video about the delays and development that led up to this moment, and maybe I will, but for now, let's just take a moment and appreciate the sight and sound of this monster lifting off.
Sound suppressor water now flowing
15.
under the ML. And here we go.
10.
Hydrogen burn-off igniters initiated. 7, 6, 5. Core stage engine start. 3, 2, 1. Boosters in ignition. And liftoff of Artemis 1. We rise together back to the moon and beyond.
Engines on the core stage and 2 solid rocket boosters now propelling the vehicle at 128 miles per hour.
And let's also take a moment and pray for Daryl Nail, whose legacy is now fumbling the word ignition during a momentous rocket launch.
Boosters in ignition.
Artemis 1 was the first lunar test flight of the Orion spacecraft, a vehicle that outlived its intended program, Constellation, and is currently intended to send humans to the moon for the Artemis program. It was launched on the Block 1 variant of the Space Launch System, a very powerful and controversially expensive rocket that utilizes a large amount of technology left over from the Space Shuttle program, including its boosters and its main engines. Even the Lockheed-designed Orion spacecraft itself has a propulsion system taken directly from the orbital maneuvering engines on the shuttle, with this first flight reflying an engine previously flown on shuttles Challenger, Discovery, and Atlantis. After several delays that included sending a red team to tighten valves on a fully fueled rocket as it sat on the pad directly next to them, Artemis 1 successfully sent Orion and 10 CubeSats toward the moon. Orion separated from its interim cryogenic propulsion stage, or ICPS, and the ICPS then released the CubeSats that were nestled in the top of it. Unfortunately, due to the many delays in getting Artemis 1 off the ground, 6 of the 10 CubeSats were already dead, their batteries running dry while waiting for launch. Orion, however, operated nominally, spending 6 days in a distant retrograde orbit around the moon before returning to Earth. However, post-flight analysis revealed significant damage to the heat shield during re-entry, caused by gas becoming trapped within it, then expanding and blowing chunks out of it. Re-evaluation and analysis of the damage has caused further delays in the Artemis program, with many questioning contractor competence, something I won't speak on personally because it's simply not my place. As of the time of writing these words, Artemis 2, which will perform a crewed lunar flyby, is scheduled for no earlier than April of 2026. Japan returned to the moon next, again in 2022, with the Hakuto-R Mission 1. A private lunar landing mission developed and operated by iSpace, it was launched on a Falcon 9 in December for a landing attempt in April 2023. Primarily a technology demonstrator, it also carried a secondary payload for the UAE and became the furthest flown privately funded spacecraft when it reached a distance of 1.4 million kilometers from Earth during its ballistic trajectory. It also carried a unique mini-rover called Sora-Q, partly developed by a Japanese toy company, which is designed to roll around on the surface in a way similar to how sea turtles move on land. However, after making its journey, the lander lost contact with mission control in the final moments of its descent.
At this moment, we have not able to confirm successful landing on the lunar surface. Our engineers at MCC continue to investigate the current status of the lander. We already confirmed that we have established the communication until very end of the landing. However, now we lost the communication.
Later analysis discovered that a faulty altimeter led to incorrect judgments of its altitude, keeping it hovering 5 kilometers above the lunar surface until it ran out of fuel and crashed. Remember what I said about things that humans could perceive with their eyes while faulty instruments cannot? Prime example right there. India was ready to try again in July of 2023 with Chandrayaan-3. Effectively a repeat of the previous failed lander with a few upgrades, this one managed to successfully touch down near the lunar South Pole on August 23rd, making India the 4th country to successfully soft land on the moon. Its rover was rolled out, moving some distance away to photograph the lander on the surface and perform some soil analysis. The lander, in addition to performing seismic and retroreflector experiments, also performed a hop experiment to test future sample return techniques. It fired its engine very briefly from the surface, rose up about 16 inches, moved about the same distance laterally, and then touched down again entirely successfully. The lander and rover weren't intended to last very long, about 14 Earth days, and everything was shut down in preparation for lunar night on September 3rd. When the sun rose again, wake-up calls were sent, but, as was expected, there was no response. After a 47-year gap, Roscosmos finally continued the Soviet Luna program in August of 2023 when they launched Luna 25. Initially designed in the 1990s, the mission suffered significant delays and threatened cancellation by the stretched-thin Russian space program. A fairly small lander, its instruments consisted primarily of different spectrometers, with several international payloads that were cancelled, both due to the delays of the project as well as by the 2022 Russian invasion of Ukraine. However, despite everything, it successfully entered lunar orbit on August 16th with a scheduled landing date on the 21st. Unfortunately, on the 19th, Roscosmos announced that the lander had encountered a, quote, abnormal situation. A command had been sent to move it into a lower orbit prior to landing, but one of its maneuvering engines didn't shut down, running for a little over 30 seconds longer than it was supposed to. This put it on a crash course, and contact was lost 47 minutes after the faulty maneuver. While a commission was formed to investigate, the LRO passed over the impact site a few days later and visually confirmed that the craft did in fact impact the moon. The next month, Japan conducted its next attempt at a lunar lander, the Smart Lander for Investigating Moon, or SLIM. Initially intending to launch in 2021, delays in its rideshare postponed it by almost 2 years until it finally launched aboard an H-2A alongside XRISM, XRISM, an X-ray space telescope. SLIM held 2 rovers along with it, a Sora Q like on Hakuto-R1, as well as the Lunar Excursion Vehicle 1 or LEV-1, which is slightly larger and moves by hopping. The lander itself is somewhat unique, with its descent engine being essentially mounted on the side of the craft. The engine would face down during landing, but once SLIM came close to the surface, it was supposed to tip 90 degrees into the correct orientation. However, during descent, something, or several somethings, went wrong. Telemetry confirmed that it had touched down successfully, but power generation was off. Eventually, analysis and photos from the ejected rovers showed that it had landed at a 90-degree angle, opposite from its descent angle. Effectively, it landed on its nose. Further analysis revealed that one of its engine nozzles had actually fallen off completely during descent, likely leading to the roll it experienced on landing. The angle was far from ideal. When the sun came up, the solar panels were on the opposite side, meaning SLIM could only generate power during the latter half of the lunar day. Despite all of this, the mission was considered largely successful. Not only was the lander operational, but it had landed within 100 meters of its target, and JAXA ranked the mission as a 60 out of 100. The rovers also worked well, acting autonomously as planned, with LEV-1 conducting 7 hops across the lunar surface before its power was depleted. Expecting to operate for only 1 lunar day, miraculously, the lander continued to respond during the 2nd day, then the 3rd, then even the 4th. However, on the rise of the 5th day, near the end of May, SLIM stopped responding. As of August 26th, JAXA has declared the mission officially concluded, not bad for landing on its side. In January of 2024, United Launch Alliance performed the maiden flight of its new Vulcan rocket. Unlike most maiden launches, which tend to carry dummy payloads due to the high failure rate of first flights, Vulcan carried 2. One was the cremated human remains of Gene Roddenberry, Arthur C. Clarke, actress Majel Barrett, and Marietta West, who was responsible for choosing the landing site of Apollo 11. The second payload was Peregrine Mission 1, developed by Astrobotic Technology, which itself carried multiple payloads for NASA's Commercial Lunar Payload Services program. Essentially, the lander was a small private venture that was partially funded to serve as the delivery method for small science and technology payloads to the lunar surface. The lander in fact carried 11 individual payloads, including 2 lunar rovers and a time capsule with contributions from 7 different countries. Vulcan's flight went unsurprisingly exceptionally well, with its tried-and-true Centaur upper stage sending the lander toward the moon. However, 7 hours after the launch, Astrobotic reported that the lander was suffering a propellant leak, making it unable to turn its solar panels toward the sun. While they were eventually able to sufficiently generate power, the leak was causing constant fuel consumption to counteract, and after 40 hours, Astrobotic announced that the lander was now a spacecraft, no longer capable of landing on the moon. Analysis revealed damage to the insulation and a possible rupture of the oxidizer tank caused by a valve that failed to fully close. While the leak appeared to slow over time, the decision was made to have the spacecraft make a controlled re-entry on January 18th, burning up over Point Nemo, a popular spacecraft cemetery in the South Pacific Ocean. In 2019, a company called Intuitive Machines was hired to provide multiple uncrewed lunar landers for NASA, which they named Nova-C. Intended to be very cheap, simple, and easy to modify from mission to mission, the first Nova-C, Odysseus, was launched on February 15, 2024, aboard a Falcon 9. After successful deployment into a translunar trajectory, the lander began to experience problems, first with its star tracker, then with a LOX cooling line. However, the lander still managed to put itself into lunar orbit on February 21st. The next day, after a last-minute software patch, Odysseus began its landing sequence. Mission controllers quickly determined that a laser rangefinder system was not working and, in a stroke of genius, decided to instead reprogram a LiDAR experiment on board to function as a new rangefinder. As far as mission control could tell, Odysseus touched down successfully, however, communications and power generation were both weaker than they should be. Eventually, analysis revealed that it was laying on its side, at least one of its landing struts had been destroyed, and it was resting on a side-mounted helium tank. It had landed faster than usual, with more horizontal velocity than intended, causing it to skid along the surface and tip over due to its broken landing leg. It was, however, alive and well, deploying the experiments that it was capable of, and after about a month, it went offline. One thing worth mentioning about Odysseus is the Eagle Cam, which I feel more spacecraft should have some variation on, because third-person perspectives in spaceflight are very important for public relations. Eagle Cam was a deployable CubeSat camera intended to be fired out from the lander during descent while being pointed toward it, allowing it to photograph the landing sequence from an external point of view. However, Eagle Cam was never deployed. Why? I'm genuinely not sure. An official statement said the CubeSat was powered down during landing but would be deployed later, however, it never was. In March of 2024, the CNSA launched Qiqiao-2, a second relay satellite to supplement the Chinese lunar program. I don't have much to say about this one. The only significant thing to mention is that it was launched into what's called an elliptical frozen orbit, carefully selected to minimize changes to the orbit over time, making it as stable as possible for a longer-lasting mission. Chang'e 6 launched next, being a sample return mission similar to the previous, though with some enhancements. First of all, it landed on the far side of the moon, and therefore retrieved the first samples from that side. Second, it also carried the Jinshan mini rover, doing a small amount of research into the lunar surface composition, as well as having a camera that allowed it to photograph the lander after it had collected the samples. The mission followed the same profile as its previous, with the lander collecting samples, then returning to an orbiter, which loaded them into a re-entry capsule, which then landed for recovery. The next mission is actually a double-header. A SpaceX Falcon 9 launched both the Blue Ghost Mission 1 lander from Firefly Aerospace, as well as Hakuto-R Mission 2 from JAXA on January 15, 2025. Blue Ghost carried a host of instruments to study methods for repelling the abrasive lunar regolith, retroreflector experiments from Earth, a computer control system designed to tolerate space radiation, and more. It spent 25 days orbiting the Earth and testing some of the experiments before attempting a landing on March 2, 2025. At 2:34 a.m. Central Time, Firefly Aerospace became the first commercial company to execute a fully successful lunar landing. Blue Ghost had touched down without any issues whatsoever. It operated for 14 days, just as intended, and even managed to provide a unique view of a lunar eclipse as seen from the surface of the moon before it went offline during the extra cold lunar night. Hakuto-R Mission 2, however, hasn't landed yet. At the time of writing these words, April 4th, the lander remains in space and is expected to land no earlier than June 6th. Having chosen a longer, lower energy trajectory, it carried out a successful flyby of the moon on February 15th, and if all goes well, will be the first fully successful Japanese lunar landing. The latest two missions to the moon were also doubleheaders, the Lunar Trailblazer and Athena, the second Nova C lander from Intuitive Machines. Launched on February 27th of this year by a Falcon 9, Trailblazer was intended to map lunar water locations and study surface variations in the sunlit portions of the moon. However, soon after a successful launch, contact with Trailblazer was lost, and it's too early to tell exactly what happened at this time. Athena, on the other hand, also tipped over. No, I'm not kidding. During its descent, a plume of lunar dust interfered with its laser and rangefinder reading, as well as causing a communications blackout. Afterwards, Mission Control found that it had landed and was generating power, but less than expected, and one of its two antennas had lost signal. The lack of accurate altitude readings had caused it to strike a plateau, tip over, and skid across the surface before coming to a rolling stop. The company's CEO described it like a baseball player sliding into home base, kicking up dust that coated the solar panels, further reducing their ability to generate power. Unable to perform or deploy most of its experiments, the lander's mission ended after 13 hours, though we did get this very cool photo out of it. What comes next for the moon? Well, Artemis, obviously, as well as China's crewed lunar program. We're in the era of Space Race 2.0, and it's unclear precisely what the future holds. The development of Artemis has been messy at best, and we're not sure what it's all going to look like when American boots return to the moon. Quite frankly, I've been talking for an hour, and in order to keep talking about Artemis, I would have to make it its own video, which again, I might do. Both countries do have the same rough plan: create a sustained lunar presence with scientific habitats, as well as eventually use the moon as a kind of space gas station to power future missions to Mars and beyond. For Artemis, that might include Lunar Gateway, or it might not. It might include the Space Launch System, or it might not. It might include Orion, or simply the SpaceX Human Landing System and the Blue Origin Blue Moon lander. Either way, things are ramping up, and it'll be exciting to see just when we'll be able to look up and see lights on the dark side of the moon.